This video is about simple pendulums, and it's an introduction to simple harmonic motion. Simple harmonic motion is the physics of oscillators. An oscillator, simply put, is something that goes back and forth. And an example here is this pendulum. You take a string, length L, and you put a mass on the end of that string, and then you displace that string. You take your hand and you bring the mass out here, not the string, but the mass. You bring it out here, and then you let go. It will start to oscillate or move back and forth about this middle position, which we call the equilibrium position. And it'll actually do so for some time. Simple harmonic motion, I wouldn't say it's defined, but it occurs when there is a restoring force that is proportional to the displacement from equilibrium. And going back to this pendulum, when the mass is over here, there's a component of gravity, a force that um, the more I bring this mass out here, the greater is that component of the force. And it wants to pull or accelerate the mass in that direction. When it's at the equilibrium position, there's no net force on it. But when the mass is over here, it has a component of the force that is pushing it back in the opposite direction and thus perpetuates the motion of the pendulum back and forth. And like we said, yeah, it's proportional to the displacement. So it's greater the further you bring it out. So for a simple pendulum, the equations that I'm going to show you here, um, specifically the period equation, works when the angle here is very short. I think it's something like 20 degrees or less. So I wouldn't say 20 degrees, but less than 20 degrees. So in other words, small angles. Let's look at some of the equations for this. Oh, first though, we need to define what period and frequency are. Period, which is capital T, mind you, is the time required for one complete oscillation, and that means cycle. So let me choose this position. I'll call this A. Okay. The pendulum must go from position A all the way over here and then all the way back to A. That would be one complete oscillation. Or it can be from this side over here. From here, it goes away, comes back. And there's actually many ways in which we can measure the period, but let's keep it simple and just say it's the time it takes to complete one oscillation. That's measured in seconds. Frequency is a related concept. It's how many oscillations occur in 1 second. And the unit for frequency is hertz, which means per second. Oh, in the next video, we will talk about spring mass systems. I won't discuss that here, although I had a picture of it. So for all simple harmonic motion, spring mass systems, and pendulums, the following equations apply. That frequency, to calculate the frequency, we just take the number of oscillations that have occurred and we divide it by the time it took for those oscillations to occur. So number of oscillations over time. Period is the inverse of frequency, so that's a 1, mind you, 1 divided by f. And it's the same equation rearranged, but frequency then can be defined as, or not defined, but calculated as 1 over the period. Okay, so we talked about this simple pendulum, length L, mass m. And for small angles, this equation can be used where the period of that pendulum is equal to 2 pi times the square root of the length of the string divided by g. If you're on Earth, then g is, we can say, is 10. And the further, so let's say you don't give it a small angle, you give it a very large angle. Um, the further this wouldn't be as accurate in that case. So it works for very small angles. Okay. That's that. Okay, cool. And I think we just have an example, and this video is almost over. We'll talk about spring mass systems, I think, in the next video. Says a pendulum oscillates 7 times in every 4 seconds. What is the frequency? And what is the period? And what is the length? Now, when they give us how many oscillations for some amount of time, well, just use number of oscillations divided by time, which is 7/4. So 7, whoops, 1.75. The units capital H, lowercase z, hertz. So it completes, 1.75 cycles every second. Part B, what is the period? Well, we have two equations for period when it comes to pendulums. Well, and spring mass systems, but sorry, it's not that one. Since we have frequency, let's just take the inverse of the frequency, 1/1.75. The period then is 0.571 seconds. Cool. And then finally, what is the length? There's only one equation with L in it, and it is period equals 2 pi square root of L over G. Make sure your radical symbol goes all the way down past G, or, to the bottom of G, all the way over. And let's solve this for L. So what I'm going to do is I'm going to rearrange this for L. I'll divide by 2 pi first. Get rid of the square root. I'll square both sides. That will be T over 2 pi squared is L over G. And to isolate L, we'll just put G, we'll multiply both sides by G. And I've run out of space to actually substitute here. Okay. Well, let's substitute some numbers. Side note, we could factor in the square. So let's say we're doing that. Might be useful later. That T over 2 pi squared, and I didn't do a good job of writing this. Here we go. It would be T squared over 4 pi squared. And that might be useful later on. But for this, all we have to do is plug in some numbers. 10, the period is 0.571 over 2 pi. Depending on the calculator you use, if you're dividing by 2 pi, for example, if you're typing it like this into your calculator, like that, and you put the 10 here, and you enter that in your calculator, it will be wrong because it thinks you're dividing by 2 and then multiplying by pi. So you would have to put in parentheses the 2 pi to show that you're dividing by this quantity in the parentheses. But if you use a fraction button on your calculator, that eliminates that problem. If you have a fraction button on your calculator. Okay, so this is 10.571, 2 pi. Don't forget the squared. Okay, the length of this pendulum is very short, 0.0826 meters, which would be about 8.26 centimeters. A pretty reasonable pendulum. Well, and I think we'll stop there for pendulums.